I want just to give you a very, very last recommendation for the course. And the last recommendation is concerning the final exam. It's my intention to organize the final exam in three parts. This is three in English, this is three in Italian, three parts. And the first two parts are theoretical part question. So you have two theoretical questions, typically one in the first middle part of the course, and the second one in the second middle part. And as a third question, you have to discuss the numerical exercise you have developed during the course. In fact, I will propose to you a number of 4, maximum 5 exercise, numerical exercise / technical report on specific issues I will assign to you. Okay? So, the exam is divided in three parts, 2 questions on theoretical issues, and the last question on the project developed. Okay? I don't know if I will assign to you in the middle of the course an assignment, an exam concerning the first part of the course, a theoretical exam, in order to take in advance the first of the 3 questions of the exam. I am not decided this. I will decide together with the development, and I hope to see you in presence here, guys. And I recommend who is able to do this to be here, present here, because you have to test the difference between life with respect to representation of the life. Okay? I think this is important for your personal learning phase. Okay? Just like in a spiritual point of view, not only practical point of view. Okay. After this speech, I want to share with you my this PowerPoint presentation. Can you see the screen? Please, one, say yes with the microphone.
Yes. Yes.
Thank you. Okay, so general issues on elasticity. The elasticity is the first discipline concerning fluid structure interaction in the history of engineering, in the history of the engineering design, and there are a lot of aspects in this discipline. But in the present course, I will propose you linear elasticity. So, what do we mean for linear elasticity? And this is the point of this introductory lesson. And I will conclude this lesson today, starting the development of a practical example that I will share with you step by step. Okay? So, first of all, I will give you some historical issues, and I will distinguish with you the difference between physical and mathematical models in elasticity, in linear elasticity. So, since this system, the elastic system, is a linear system, we were talking about what is the stability, what is the response problem for this linear system, the elastic system. I will show you some experimental facts on elasticity, and then at the end an introductory example that I promised to you to develop. And this example will consist of the vibration of a simple supported panel undergone to an external supersonic flow. What about the emphasis of this conversation? The emphasis is on the point. This discipline is not specific for special application. Now, the approach that I want to propose you is the approach of a general theory of elasticity. So we will develop together general instruments for studying elasticity. And of course, our attention will be so focused on aircraft fixed wing elasticity. And so we don't have special cases, special problem, a simple supported beam, 2 degrees of freedom system. No. The theory is general, and eventually we will apply this on special problem if you want. But the concepts are absolutely general. This is for linear. What about the nonlinear? The nonlinear is very, very important. Very, very important. Everything we see is nonlinear in our life. When you have the experience of a microphone close to the speaker, you have a very, very high frequency sound, like, okay? This is a common experience. And this common experience of the microphone closer and closer to the speaker is a very standard example. I'm having my lesson at the moment. Bye-bye. This experience is a standard feedback experience. But your hi-fi amplifier typically does not crash at this. Because the linear theory, when you have an unstable system, says to you that the response is an envelope of an exponential by a harmonic function. This is the result of linear theory. So if you have an exponential, after a reasonable period of time, you will have a crash because you have a growing response. But typically, the speaker don't crash after a feedback experience. Typically. It could, but typically not. And the fact that you can't see, in that case, a crash, but just a high-frequency sound, like, this high-frequency sound is a sound characterized by the frequency and by a limited amplitude. What does it happen? You have an instability, in that case, given by the feedback. Your system is affected by this instability. Your system is going to have a larger and larger response. And in this time, your system is linear. But after a time, waiting for to have a higher amplitude, your system is able to show to you the nonlinearity. So the nonlinearity are actually turning on. And what is the role of this nonlinearity for the system? The role of the nonlinearity when are present in your system is when you are very, very lucky to bring the linear part to be limited. So, in general, the nonlinearity may be stabilizing for your system. This is the reason because when you have an instability, a closed loop instability, you may don't see necessarily a crash. You may experience just a high frequency sound, just in the case of the microphone, the speaker. Okay, so when you see an unstable oscillation, and you see that oscillation, you probably are observing a system already in the stability regime in a linear point of view, but probably the nonlinearity part is active, and this nonlinear part is actually limiting your response. Okay? So this is the fundamental rule of the nonlinearity. But the role of the nonlinearity is not necessarily a safety rule. Okay? Another practical example. When you compress a plate, practically, you may have a static instability, as most of you know, the classic buckling for the plate. Okay, what about the linear theory for the buckling? If you are in the buckle after the critical load, your system is able to diverge. And the evolution of the divergence, as most of you know probably, is a linear trend. Okay? Linear means that the amplitude increases in time linearly. But what you observe in practice is you compress your structure and you have just a curved final configuration. Okay? And so what is happening? The same history. The plate is compressed, the plate starts to diverge, and while it's diverging, the nonlinear part, for example, given by the nonlinear kinematic of the plate, that you are typically, okay, avoid the nonlinear effect, avoid, but these effects are present. And for example, for a compressed plate, you have that the transversal fiber of material may be stabilizing for the longitudinal one, just like to have a spring bed. So you compress your plate, the plate is going to be a buckling, but the other region in nonlinear, or absolutely in nonlinear region, is able to keep the response limited. And what you see when you compress the plate, and you are able to see this deformation as a finite deformation. And this is the effect of nonlinear effect. But remember these important issues. The limit denoting the boundary between the stable and the unstable region is given by the linear analysis. The behavior after this limit is given by the nonlinear analysis. This is the point. And this behavior may be described, for example, just written here by the bifurcation theory. Okay? Okay, so some historical issues. Aeroelasticity, as definition, studies the phenomena arising by the interaction, force exchange, and displacement shared in the interface between body and floor. Guys, in the interface, the only way for having an interface between a solid and a fluid is represented by only two actors, and you may change one of these actors for describing the interface. Displacement and force. Displacement and force. The force are exchanged in the interface, fluid and solid. The displacement of the interface are shared between fluid and solids, and in the interface you have the same displacement for the particle of fluid and the particle of liquid. This is the interface description, okay? And through this interface, you may describe an energy crossing between the fluid and the solid. Exchange of energy.
Professor,
yeah?
From online, we cannot see any slides. We see a blank page, a blank presentation.
Is blank actually?
A white presentation.
It's quite white, quite white. Can you
White.
see title? Can you see a title?
No.
Okay,
No.
I will restart the presentation.
Okay, thank you.
But can you hear me in the speech?
Yes, now.
Okay. So okay. And now can you see this?
Yes, now is visible for me.
Okay.
Summary of
definition and historical issues. Can you see it?
Yes.
Okay, thank you. Okay, so this is the definition. And what happens? If a deformable body is emerged into a flow, indeed it is propelled by a powerful engine. Don't forget this. The flow itself might be source of a potential infinite energy that instead of propelling the body might induce destructive consequences. This is Flutter, for example. A standard way for describing this instability is the following graphical representation. Here you have a triangle in the vertices A, I, and E. And in this famous triangle, which is also known as Scholar triangle, you have aerodynamic here, inertial force, and elastic force. This is the standard triad in aeroelasticity. The interaction between elastic force, inertial force in a deformable body, and the aerodynamic force. You may study in physics also a partial interaction between these disciplines. For example, if you study the interaction only between elastic and inertial part, you have here the mechanics of vibration. This edge here is characterized by the vibration study. If you study the interaction between aerodynamic and inertial force, avoiding the deformability of the body, so considering a rigid body, you have the flight dynamics, okay? Also known as dynamic aircraft stability in this edge here. And finally here you have a very special discipline characterized by the aerodynamic and the elasticity, but avoiding the inertial force, so avoiding the motion. So this is also known as static aeroelasticity. So this here is the static aeroelasticity, and considering the overall triangle, you have the elasticity, the classic elasticity. And if you consider this standard classic elasticity, you can study inside here flutter and dynamic response of the elastic system. F for flutter and DR for dynamic response. If you consider only the indeed the correct way for discussing this is the following. You should divide this A in two parts: the static aerodynamic and the overall static and steady aerodynamic. If you consider static aerodynamic, S for static and E for elastic, you may study as the static subspace of the elasticity. The static subspace of elasticity is the subspace where static instability occurs. Static stability is something like the buckling. Buckling is static instability. And the static stability for the elasticity is the so-called divergence. Here you can see two letters for instability. This D is for divergence, and this F is for flutter. So flutter is a standard dynamic instability given by the presence of inertia, elasticity, and aerodynamics. The divergence is an instability only given by elasticity and steady aerodynamics. If you like the control system theory or the mathematics, the difference between divergence and flutter is very, very, very easy to be understood. The flutter is a dynamic instability and consists of the crossing of the imaginary axis by a couple of conjugated poles. The divergence is another kind of instability characterized by the fact that the imaginary axis is crossed by a pole crossing the origin of the complex plane. Okay? So in the flutter you have an oscillation in the stability. In the divergence you don't have oscillation. Therefore, imagine to have a plate like this. You see this plate? Okay. Now, please don't say nobody. I am moving my mask for a second to show you a static divergent instability. Static. This is the divergence. At the origin of this instability, when the amplitude is not so high, you have a crossing of the origin of the axis. And this is the divergence. But the divergence is not the only static phenomenon. You have also, for example, the efficiency of the control surface, the aileron reversal, and the static aircraft stability. Okay. As very, very final commenting of this figure, in the limited range of use of inertia and aerodynamic, you have DS, which is the study of dynamic aircraft stability as rigid body, not deformable. Okay? Okay, this is the domain of application of aeroelasticity. An interesting issue is that the aeroelasticity influenced the historical region of the aviation. So in 1904, Wright brothers biplane solution anticipated Mr. Langley monoplane solution, because Langley dimensioning design was based on elementary static torsional wing analysis, not considering the aerodynamic load variation as effect of torsional deformation itself. Langley designed the monoplane assuming that the torsional stiffness of the wing can be simply applied as a static theory as a consequence of the application of the momentum of the pitching moment given by the aerodynamic force. But after the application of the aerodynamic force, the wing is deformed, and you have to consider this deformation for recalculate the lifting force. You have to do, but if you don't do this, your calculation is approximated. And this was the error of Mr. Langley. And what about the solution of the Wright brothers? Biplane, which means improve the torsional stiffness of the wing. Okay? This is the explanation of what I've said before. And this is the experience of the, you know very well this picture here with the Wright brothers. Excuse me, just a second. Okay, excuse me. Noise in the room. And this is the monoplane, Langley monoplane. The interesting historical consequence is that, you know that there are many NASA centers in the United States, many centers, Houston, but there is a very important NASA center in Norfolk, Virginia. If you are a fan of the TV serial NCIS, Norfolk is the city where there is the US Navy in the West Coast. And in this strategic city, there is a NASA center known as Langley Center. In NASA Langley Center is the most important center studying fluid structure interaction. So this is just a prize recognized to Mr. Langley for his efforts. So we plane flew before then the monoplane, as you know. And this is the crash here of the monoplane. The point of improvement of the velocity was done in the Second World War, where the unstable aerodynamic modeling was developed and the design capability increased, and the use of metallic wing box structures allowed in the 30s to successfully introduce the use of monoplane configuration again. So there was a recovery of monoplane configuration after introducing the metallic aluminum together with the concept of wing box, which is, as you know, a fundamental concept in aeronautical structures. Okay, with the wing box concept, the torsional stiffness of the wing is highly improved, but keeping very, very light solution. Okay, and this was the key, but this is not the only key for improving of the elasticity. There is another important point in this development. The important point is the point I tried to propose to you the day before yesterday, and the point is unsteady aerodynamic. What is the unsteady aerodynamic? You have two disciplines to be coupled, aerodynamic and structure. Okay? The structure is described by you in linear sense in dynamic way, including the inertial effect and the elastic effect, two components, inertial force and elastic force together. And this package of description is able to give you a mathematical model, which is a second order time derivative model. Okay? So you have a dynamics. You have the dynamics of the system. But what about the dynamic of aerodynamic? This is a famous sentence in my course. I am the author of this sentence for the student. What is the dynamic of the aerodynamic? We discussed at this point the day before yesterday, because the day before yesterday, talking about the D'Alembert paradox, we decided that the aerodynamic system is not a simply proportional system, in the sense, if you have in a steady case the lifting force proportional to the angle of attack, if you have, for example, an unsteady angle of attack as input, so you are moving, for example, imagine to have a wind tunnel, you have a rigid, okay, it's okay, rigid, a rigid model, and you move this rigid model arbitrarily. So you have an alpha angle function of time. You impose this as input. You are modifying the boundary condition in this simple way. Question. Imagine to be to have the capability to measure the lifting force as a function of time. Can you write lift is equal to 1/2 rho u infinite CL by alpha function of t, period? If this were true, the dynamic of the aerodynamic is just proportional. Okay, in time, you have to take your time boundary condition and obtain the solution. You can obtain this solution for a static case, and you could obtain the solution for the static case just multiplying what you have obtained the static by a function of time, and that's it. But this is not true, unfortunately. The dynamic of the aerodynamic is more complicated. Is a special kind of system. In linear case, in linear framework, is a special kind of system. And we will study this kind of system together. Okay? So I have expressed this concept here. The aerodynamic is not a simply proportional time-dependent operator. In other words, a steady aerodynamic is not a trivial extension of the steady aerodynamic. And so the unsteadiness of aerodynamic cannot be reduced to the presence of equivalent stiffness or damping or inertial effect as the vibration elastic body. What I mean in this sentence here is the following. If you want to describe the aerodynamic force, question, can you imagine to express this aerodynamic force as the application of a mass matrix applied to the acceleration vector plus a damping matrix applied to a velocity vector plus a stiffness matrix applied to a displacement vector? Is the aerodynamic something similar to a structure? Answer, no, unfortunately no. And so there were people studying this, famous people like Theodorsen, von Karman, Glauer, Pran, that study how to correctly study the unsteady aerodynamic. The other development, and this is about around 2014. In the 15, the design trend on building lighter and lighter aeronautical structure made them more and more flexible. So in this age, the elasticity accepted the challenge of the jet propulsion here. So higher velocity and lighter structure. This is a problem. Okay, and this was a very important period in the development of the elasticity theory, and in the same period there was also the problem of and the development of helicopter machine, which is another very important issue for the elasticity, as you can imagine. What about the problem of helicopter? Let me spend a few words about the complexity of helicopter aerodynamic with respect to standard wing aerodynamic. When you have a flying aircraft in steady motion, after the trailing edge, you have a wake, and the wake is just a contact discontinuity. In the potential theory world, this discontinuity is a zero thickness plane with vorticity. In order to have the lift on the aircraft, you have to consider this vorticity, the effect of the vorticity on the aircraft, Biot-Savart law, and this effect will give you the final lift. So the role of the wake is essential for generating lift, steady lift, and unsteady lift. Now imagine a helicopter. What happens to an helicopter? Imagine to have an helicopter in hovering, fixed in the sky, okay? Fixed. And the blades are running. How the helicopter is able to be sustained and fixed in the... Physically, you have only one possibility. The blades are able to push the air down, and the helicopter keep winning the weight force of itself. Okay, this is the physics. And what about the wake of the blade? The blade is moving around, and the trailing gauge is able to shed this vorticity, to shed this contact. So, how can you imagine this wake as generated by the turning blade? This wake is just an helicoidal region, okay? In fact, and this helicoidal is just like a very special kind of pasta, as known as fusilli. It's just like a fusillo, okay? The blade is moving. This wake is moving together the wake. If you remember a property of the contact discontinuity, you studied gas dynamics. The contact discontinuity has the property to be not penetrated by the fluid. But in the contact discontinuity, you have only shear, not penetration. And therefore, you have a fusillo rotating, and this fusillo is just like a screw pushing down the air, and the helicopter is up. Okay? This is the aerodynamic of the helicopter in a very, very fast way. And this gives you an idea of the complexness of this kind of aerodynamic. Because in order to evaluate the force on the blade, you have considered the effect of this vorticity, complicated geometry, up to the blade. Of course, there are also elementary theory. If some of you will follow the helicopter course here, during this academic year, will discover this kind of aerodynamic. However, the helicopter 15, 16, and in 16, 17, this concept, this coupled concept, was also completed with thermal effect. If you have a re-entry aircraft, you may have a very, very high temperature field, and the change of temperature may cause another important effect on structure and aerodynamics. So you have so-called aerothermodynamics, or also aerothermoelasticity. Okay? These are all evolution of standard aeroelasticity. In 1919, also were developed other discipline connecting the maneuverability concept typical of flight dynamics with aeroelasticity, and this is the aeroservoelasticity as well. Okay, and so there was just like a cross-fertilization in other engineering fields, like civil engineering. So TV towers, offshore platform, skyscrapers, any kind of suspended bridge, any kind of civil engineering structure undergone to wind are subjected to flight structure interaction, which is something originated by the elasticity problem. Of course, we have also finally some influence on mechanical engineering, turbine, compressor blade, wind turbine, flexible vessel, and so on. There are a lot of, but this kind of issues are not aeroelasticity, are properly fluid structure interaction problem. And the elasticity is just like the historical father of all this kind of present problem. Okay, let me do a comment with you, just taking a comparison between this old generation civil aircraft. This is a Boeing 747. We are talking about 16 aircraft. Look, this aircraft. Okay, and this is a Boeing 787 aircraft. Look this picture here. I compare this picture with the previous one. Look the difference. Here you can see 14 years development in aircraft design. Okay, apart the number of propeller and the number of unuseful and redundant sustaining aerodynamic surface down here. So apart the cleanness of the new aircraft generation, look, this clean wing with respect to this wing here. The most important issue on my point of view for you is one. Can you see this point of view? This, compare this with this. Look this wing deformation. And look to this wing deformation. Practically, you can't see deformation here. You can't. Because all the effort of people, of designer people in that age was to avoid any kind of deformation. Actually, we are able to control this deformation. Actually, we are able to design the aircraft in flight condition, controlling and considering the deformation effect. But we can do this because we are measured in a realistic point of view for estimating in design phase this kind of effect. In the 747 age, people were not able to do this. Now, people can do. And people are good after this course. Okay? So, this is the order of magnitude of the typical deformation in the present aircraft. You have, this is the neutral axis and the deformed axis, and this is the standard in operative condition, which is about for 787 or about 10 feet. At 26 feet is the maximum allowed displacement. Okay? Okay, now, after this historical, I want to give you the main concept of the theory we will develop. Mathematical model and physical model for linear elasticity. Physical model, structures, linearly elastic solids. Aerodynamics, sorry for this F, ambiscus, unsteady, attached, and linearized flows. Okay? Ambiscus, but unsteady, please, but unsteady, please, but unsteady, because unsteadiness is fundamental to be described in order to represent this kind of phenomena. If you don't use, if you perform an elastic analysis and assume as lifting force the force as given by the steady theory, you will produce a very high error, as you probably realize by your project. So, in the mathematical point of view, you have a closed loop system, you have a structure here, structure block. In the structure block, you have an input. As output, you have displacement. This displacement vector is represented by Q tilde, but with tilde will indicate Laplace on Fourier transform quantity. Okay? This is my convention. This convention is assumed by many people, and this is also my convention. So, this diagram is in Laplace domain or frequency domain if you prefer. So you have the structure, you have the output, the displacement. The displacement of the body is the input of aerodynamic. This displacement is a function of time or function of Laplace variable. So you have an input for the aerodynamic, and the aerodynamic will give you force. These forces are represented by E. Note that these F here are the external force, the really external force to the block. But this here, E, is the internal one given by the aerodynamic, which produces this force as consequence of the motion elastic motion of the body. So you have a closed loop here. You have a double summation of this internal given by the aerodynamic E and the external given by F. Okay, this is the model. After this model, you have to perform a space discretization. This is a very, very important point. I want to be clear on this point. For describing structure and for describing aerodynamics, typically your mathematical model is a PDE model, partial differential equation in general, space and time. But we will work on space discretization, both for structures and fluid. After our space discretization on the structure, we have the equation of finite element method. You have a second order equation with the mass and stiffness methods. This is the result of space discretization. Here I am voluntary, vague, and generic. I give you the general idea, but the fundamental idea. Don't care about the detail. We will have time for all the details you need and you want. Okay? So after the space discretization, you have finite element for the structure, and we will have boundary element method for the aerodynamic. Scandal. CFD people. Oh shit! Boundary element method. We want finite volume. We want to have fill the space of a mesh. Everything. Okay. For discretizing the aerodynamic, you can mesh your field, the aerodynamic field, everywhere, and on the body will. But I will show you, and I will convince you that if you have a linear and viscous steady attachment in as a flow, you have a potential flow which can be discretized only on the boundary of the body, period. Okay? You can do this. You are authorized to do this. This is a focal point. Okay? So, space discretization, structure, and fluid. At 3 o'clock, I can have a break if you want, before talking about mathematical model and close this introductory lesson. Okay? So, have a break. Is everybody okay? For people